All right, geometry. Hey, I'm coming to you here from my backyard where I'm a little bit under the weather, so my voice is going to sound probably a little bit different, but enjoy the background sounds of the birds in the neighborhood. Here we go, 8.3 special right triangles. So you're going to want to pay special attention to this, especially if you're going to go on to higher maths like pre-calculus, because we will use this idea a lot in pre-calculus. But today you're just going to learn a couple of patterns that arise with specific types of triangles. They're called special right triangles. There's really only two of them, so there's two patterns to learn with the two different special right triangles. And yeah, let's just get into it. So here we go. There are relationships between sides and angles of triangles. If you haven't figured that out already, hopefully you figure it out this lesson. So if you think about it, this says, what happens to the non-right angles when a leg is lengthened in a triangle? So if you were to think about that, if you have a right triangle, so you have a right triangle, right? It says, what happens to the non-right angles when a leg is lengthened? Okay, so let's just look at this one here. This is a right triangle, right? So if you look at the non-right angles, what that's talking about is it's talking about this angle right here, this angle right here. Okay, so let's extend that and let's just think about what happens. Okay, so if we extend a leg out like this, okay, notice what happened to this angle. All right, so it's the same kind of triangle. I extended this thing out. Notice how this angle got much smaller, right? And the angle up top got much bigger. So that pattern arises over and over and over again. Here you'll see this. So there's definitely some kind of relationship between extending legs on a right triangle and the angles that are opposite of those legs. So that's what we're going to unpack today. Here's the first one. It's called the 45-45-90 triangle theorem. Okay, this one says that in a 45-45-90, the legs are congruent, and the length of the hypotenuse is the square root of 2 times the length of a leg. So what I want to show you is if you have a 90-degree angle here, okay, and this happens to be 45 here, and this happens to be 45 here, since there's a relationship between the angles and the sides opposite, if the angles are the same, like they are here, this is the only case in which they're the same, by the way, then the side opposite would be the same length on a 90-degree triangle, okay? So if this was 2, for instance, this would be 2. Now, the hypotenuse is always going to be the square root of 2 times whatever this is. You'll see that because well, you can prove it to yourself with the Pythagorean theorem. So with the Pythagorean theorem, we say 2 squared plus 2 squared equals, c squared, right? So if you did this out, you would get 4 plus 4 equals c squared. We get 8 equals c squared. And when you solve this, you get c is equal to the square root of 8. Well, if you simplify the square root of 8 and you take the perfect square out of there, which you need to be comfortable doing here soon, the perfect square in 8 is 4. So this is the same thing as the square root of 4 times the square root of 2. If you take the square root of 4, you get 2. So 2 root 2, or the square root of 2 times the side length, will always be the pattern that arises. Okay, so what I like to do when I memorize this, I would just do this little jingle in my head where I'd say, okay, with the 45-45-90, it's a 1-to-1 to square root of 2 rule, where the hypotenuse is always the square root of 2 times whatever the length is. All right, so 1-to-1, meaning if we know one side length, then it's a 45-45-90, and you know the other one. So if this was 2, this has to be 2, and this would have to be 2 times root 2. All right, so let's just go ahead and try this out. By the way, if you know that this is a 90-degree angle and this is 45, you know that all together has to equal 90, so you could figure out very easily that that's equal to 45. Here, if you have the side lengths that are the same, 5 and 5, you know that the opposite angles have to be the same. Since this is 90, we know those have to be 45s. Okay, so I'm just kind of filling in some things that I already know. Same kind of is true on 1C. Okay, so these are all 45, 45, 90 triangles. Hopefully you're able to see that. Now what I'm going to do is solve each one of them. Okay, so again, we're going to just use our rule. So if this is 4, I know that this length has to be 4. Okay, the easiest thing to do here would be to say, okay, I'm just going to follow the pattern that I know is true and say that x is equal to 4 times the square root of 2. If you didn't trust the pattern and you wanted to use the Pythagorean theorem, you could say 4 squared plus 4 squared equals c squared. Okay, so when you do this out, you get 16 plus 16, which is 32, equals c squared. So c is equal to the square root of 32, and some of you are saying, well, that's not the same thing as 4 root 2, but it is. If you take the perfect square of 16 out, it's the same thing as square root of 16 times the square root of 2. Square root of 16 is simply 4. Okay, so that actually reduces down to 4 root 2. All right, so with 1b, same kind of deal here. Now I'm not going to go through the whole Pythagorean process. I'm just going to, I'm going to use my rule. So I'm going to say, if this is 5, since x is the hypotenuse, it has to be 5 times root 2. Simple as that. Now, 1c is a little more challenging. Okay, so we know that x is equal to the leg, right? The leg of this 45, 45, 90, which is 7 root 2, times root 2. Okay, that's what we've been doing all along, is we've been multiplying by root 2, by root 2. We're going to do the same thing here. But when we do that here, we have root 2 times root 2, which is simply 2, because root 2 times root 2, side note, is equal to root 4. But the square root of 4 we know is already 2. So this is saying, okay, this is the same thing as 7 times 2. So x then is equal to 14, and I'm done. All right, so that's using the 45, 45, 90 rule. Here it says find the leg length of a 45, 45, 90 right isosceles. Set the hypotenuse to equal the leg length times root 2. Solve for x. Okay, so if a hypotenuse is equal to 9, we know that the leg length is going to be equal to x times the square root of 2 of that thing. Okay, so we know that 9 is equal to the square root of 2 times whatever the leg is. So again, it's leg times root 2 equals hypotenuse, and we're just going to plug in what we know. All right, so here we know the hypotenuse, and we're looking for the leg. So again, the leg times root 2 equals the hypotenuse. So I can say, okay, well, my leg here is x, right? So I could say the leg times root 2 is equal to the hypotenuse, which is 5 root 2. Hopefully you can see here that x then would just have to be, you could see that if these things are truly equal, x would have to equal 5, right? But if you didn't know that, you could divide both sides by root 2. And when you do that, you get x is equal to, these cancel, x is equal to 5. All right, same thing here. We could say x, the leg length, times root 2 has to equal 18. Okay, we know that because of the pattern, right? The hypotenuse is equal to the leg times root 2. All right, so to solve this, we're going to divide both sides by root 2. X then is equal to 18 over root 2. Now, side note here, we don't, by convention, leave the square root of 2 in the denominator. So to get rid of it, we're going to multiply this by root 2 over root 2. That's a well-chosen 1. It's equivalent to 1. And so when I do that, root 2 times root 2, we've already proven in this video, is equal to 2. So what I end up with here is on the top, I end up with 18 root 2, and on the bottom, I have a 2. Okay? Technically, there's nothing wrong if you wanted to put this in a calculator and get a decimal here, but I want you to practice your radicals. This is the same thing as 18 root 2 over 2 is the same thing as, well, 18 divided by 2 is 9, and those are, since this is all one term, I can simplify that. This is the same thing as 9 root 2. Okay, so that's 2b. And if you have problems with the simplification piece, we'll do some more examples like that in class, but just try to practice that. If you give me the decimal, it's not necessarily wrong, and I'm not sure what's in the back of your book, but it's a good idea to use radicals when you can. which is this whole lesson. The second part here is the 30, 60, 90. Okay, so this pattern's a little bit different. This one is, it says the length of the hypotenuse is 2 times the length of the shorter leg, and the length of the longer leg is always the square root of 3 times the length of the shorter leg. Okay, the way that you can remember this is the hypotenuse will always be the longest side, and 2 times, when you do the square root of 3 out, it's like 1 point something, right? So this is actually less than 2 times. So your hypotenuse will always be the longest side length, which will always be the 2 value. So what this means is, if you have a right triangle, and this is a 90, and let's say this is 30, and this is 60. Okay, it's only on the 30, 60, 90. If this is the case, the side length straight across from my 30-degree angle will always be my x value, or my 1 value. Okay, this is the 1 to 2 to square root of 3. Straight across from the 90 will always be my 2 value. So here I'm just going to say, okay, it has to be 2 times whatever that 30-degree angle was. And if I call it x, I'm going to call it 2x. Okay, and then across from the 60-degree angle, this will always have to be whatever x is times the square root of 3. That's the pattern. Okay, so the little jingle for this one was 1 to 2 to square root of 3. With all 30, 60, 90s, it's going to be a 1 to 2 to square root of 3. All right, so here's some rules to remember if you need to jot these down. So the long side is always equal to short side times root 3. The hypotenuse is always equal to the short side times 2. And the short side is always equal to the hypotenuse times 2. Remember that we have a pattern here with all right triangles. We know that if a side length changes, the angle changes as well. We're just following the pattern. So let's try it out. Example 3, and then I'll let you guys go on your way. So these are all 30, 60, 90s. They don't always give that to you, but like notice in 3B, if this is 60 and this is 90, we know this has to be 30 by default. So let's go ahead and do these. Okay, so the most important thing here is identify the 1. All right, so the 1 in the 1 to 2 to square root of 3 is always going to be across from your 30. So here in this case it is x. Okay, the long side here, we know this is always going to be equal to the short side, which is x times root 3. And we know that the hypotenuse, which is across from the 90, will always be equal to the short side, which is x times 2. Okay, so now I can use that to solve this. All right, so let's just set these things up. We could say 12 is equal to x times root 3. Okay, if I want to get x by itself, I have to divide by root 3 on both sides. All right, so when I do that, I get x is equal to 12 over root 3, but I can't leave it like that, right? So I have to multiply by root 3 over root 3, which is equal to 1. And I'm left with 12 root 3 over 3, but that simplifies to simply 4 root 3. Okay, so I know that my x value is equal to 4 root 3. My y value is equal to whatever the x value was times 2. Well, I now know my x value, it's 4 root 3. So if I take 4 root 3 and multiply that by 2, what I end up with is simply 8 root 3. And that one's done. Excuse me. So now, let's do the same thing with 3b. So across from the 30-degree angle, that's our 1, right? So that one's just x, which is nice. I know that my hypotenuse is going to be equal to 2 times that. So I can say, okay, so 10 is equal to 2x. And if I solve this, I would get x is equal to 5. And then I can say that my y value is equal to the square root of 3 times x. Okay, I know that x is equal to 5, so I can just plug that in. So I can say y is equal to 5 root 3, and I'm done. All right, let's try another one here. So straight across from my 30, I get 21. That's my shortest side is 21. Okay, so again, my y is equal to square root of 3 times x, or times the 1, I should say, which in this case is 21. So y is equal to 21 root 3. Okay, and again, if you guys don't want to use these patterns, if you kind of have to find one of these, but once you find one, you could use the Pythagorean theorem here if you wanted to solve for x, but it's much easier if you just knew the pattern. We know that x is equal to 2 times the shorter side. The shorter side in this case is 21. So 2 times 21 equals x. X is equal to 42. All right, you guys, I know this was a little bit rushed, and I know you probably need some practice with radicals and simplifying them, but that's what this lesson's for. So please put in the time, try to simplify your radicals, pull out your perfect squares. Remember to get your radicals out of the denominator by multiplying by a well-chosen 1, and we'll do some more of this in class, and we'll see you guys next time.